This is my second part. I'm going to talk about reaction types. And I know I moved through that very quickly today, but I want to do this review so you can go over it and just as some review. Again, we're gonna introduce now the states of matter. And the symbols S stands for solid. Your book uses the letter C. Uh, Lowercase cursive L represents liquid. Your lowercase g represents gas, and AQ represents aqueous. And aqueous just means it's been dissolved in water. We're going to go through some types now of reactions. The first one I want to talk about is synthesis, also called combination reaction. The general format of this one, you have A plus X yields AX. And you have an element plus an element yields a compound. And so in the first example here, I have sodium and my chlorine. And so this really comes down to fundamental nomenclature. So to think about it, when I bring sodium and chlorine together, I have to bring them together in the correct ratio. So my sodium's in group 1, it's a +1. My chlorine's in group 17, it's a -1. They come together in a 1-to-1 ratio. Then I go back to sodium, it can stand alone. Chlorine is diatomic, so it's Cl2. And then I just balance it. My next one, calcium and oxygen. Calcium's in group 2, it's a +2. Oxygen's in group 16, it's a -2. They come together in a 1-to-1 ratio. I go back to my reactants. Calcium can stand alone. Oxygen is diatomic. So I just balance it. Letter C, lithium's in group 1, it's a +1. Sulfur's in group 16, it's a -2. I therefore need 2 lithiums to zero out my sulfur, so it's Li2S. I go back to my reactants. Lithium can stand alone, and sulfur can stand alone as well. And then I balance it, and I need 2 lithiums. My last example, aluminum's in group 13, it's +3. Oxygen's in group 16, it's a -2. Do the crisscross method, I get aluminum oxide, Al2O3. And then I go back and I balance it. So it is a 4 moles of aluminum, the 3 moles of oxygen, the 2 moles of aluminum oxide. I won't worry about the state of matter when you do this on the test. Another type of synthesis or combination reaction is when we have a metal oxide plus water will form into a metal hydroxide. So it's easy if you recognize this because you'll see that the metal is going to, your product here is just a metal joining up with a hydroxide. And if you remember, hydroxide is OH with a -1 charge. So if you know the charge of your metal, it'll be easy bringing them together in the correct ratio so the charges add up to 0. This first one, sodium oxide plus water, well, sodium's in group 1, it's a +1, so sodium hydroxide is a 1-to-1 ratio, NaCl, and then you'll just balance it. My second one, calcium's in group 2, it's a 2+, so I need 2 hydroxides to zero it out. Remember, you put parentheses around your hydroxides, then you can just balance it, and it's fine, it's already balanced. My last one, my aluminum's in group 13, it's a +3, so I need 3 hydroxides to zero it out, and then I'll just balance it. So these are examples of also synthesis reactions. Now if I take my synthesis reaction and I reverse them, I now deal with my next type, which is called a decomposition reaction. My decomposition reaction, I will take AX yields A plus X, and my compound breaks down to an element plus an element. Decomposition are easy to recognize because the reactants, there's only one reactant, and there's only one thing that reactant can do, and that is break down. In this one, you see a simple binary ionic compound. All you're going to do is separate out the cation and the anion, and when you separate the anion out, remember your diatomic elements. So fluorine breaks down to, my ferric chloride breaks down to iron plus chlorine, which is diatomic, Cl2, and then I just balance it. My cuprous bromide breaks down to a copper, and then bromide changes bromine by itself as a Br2, and then I just balance it. My magnesium oxide, my oxygen is diatomic, so it breaks down to Mg plus O2, and then I just balance it. So this is your first type of decomposition reaction. There's a second type of decomposition reaction. This is when I had my metal oxide plus water form metal hydroxide. Well, if I start out with a metal hydroxide, it's going to go in reverse and break down to a metal oxide and water. Now I realize my metal is now going to bind up with an oxide. Oxygen is in group 16, it's a -2. So my beryllium in this situation is a +2. So it comes together in a 1-to-1 ratio, and then I add water. My next one, my manganese, well, it can be a 2 or a 3, but it's bound up. I need 2 hydroxides to zero it out. That means it must be a manganese 2 or manganese. Therefore, it's a +2, -2 will come together in a 1-to-1 ratio as well. Letter C, my copper comes together with a 1-to-1 ratio with hydroxide, so it must be a +1, copper 1 or cuprous. Therefore, I'm going to need 2 of them to zero out my oxygen, and I will have to balance this one. The second type of decomposition. The third type of decomposition is where you take a metal chlorate and it will break down to a metal chloride and oxygen. So you're just stripping off the oxygen in this one. So again, your metal chloride, chloride's a -1, so make sure your metal and your chloride zero each other out. So our first one here, potassium chloride, breaks down to potassium chloride, +1, -1, and then oxygen, which is diatomic, and I balance it. My second one, zinc chloride, breaks down to zinc chloride. Now I need 2 chlorides to zero out my zinc, and I have oxygen, and I balance that as well. So this gives you an example of 3 types of decomposition reaction. The next type we're going to talk about is double displacement, also called double replacement. And what we have here, what makes this one stand out is you have two ionic compounds on your reactant side. And what's going to happen, the cations are going to trade places with they're going to exchange the anions. One thing you need to know here with the double displacement are the solubility rules. And when I say, when the first one reads, for example, all alkali metals, metal compounds are soluble. What it means by soluble, it means it's going to stay dissolved in liquid, so it will remain aqueous. But once you get down to number 4, it says most hydroxide compounds are insoluble. What that means is that it will form a solid and it will fall out of solution as a precipitate. So let's move on to double displacement. I have just a couple examples. We'll do more later on. Now, if I break down my double displacement, what I encourage you to do is strip it down to the ions, rearrange it, and bring it back together again so the charges add up to 0. So what's going to happen is my hydrogen is going to leave the chloride and bind up with the hydroxide. My sodium is going to leave the hydroxide and bind up with the chloride. So we break it down to the ions here. We see that my H plus and OH minus forms water. My Na and Cl form sodium chloride. Now, this is the only one I will expect you to break it down to the ionic. And as you see here, the aqueous are the only ones that break down to the ionic. Solids and liquids will not. And so my water stays intact. Next, I'm going to ask you to get rid of what we call the spectator ions. And those are the cations and anions that show up on both sides. In this situation, it's chlorine and sodium. And when I get rid of the spectators, then what I have remaining is what I call my net ionic equation. And so in this situation, my spectators, sodium chloride, are gone, and I end up with H plus OH minus yields water. This is an example of a neutralization reaction. If you remember, went back in biology, H plus was a strong acid, OH minus was a strong base. So that's exactly what's happening here. My strong acid and strong base are actually neutralizing each other and forming water. Next one, I have silver nitrate and barium chloride. Again, if I were to break them down, I know it's the final product when I balance it, but if I was to first break them down, I'd have silver +1 binds up with the chloride -1 and forms silver chloride. My barium +2 joins up with the nitrate -1, so I need 2 nitrates to zero it out. Then I'd go ahead and balance it. But this one, again, double displacement, I will expect you to break it down to the ionic equation. And then remember, the only ones that stay intact are your solids. And if you remember back, silver chloride will be a precipitate. It is insoluble. So if I get rid of, once again, my spectator ions, which in this situation are my barium and my nitrate, and then bring the remainder down, I would have 2 silvers plus 2 chlorides yields 2 silver chlorides. And yes, this should be simplified down to a 1-to-1-to-1 ratio. But in this situation, my spectator ions are seen as my barium and my nitrate. We'll work more on these double displacements later on.